Okay, thanks, Tommaso, for presenting today. We see your tablet starting. Okay, and a very nice title.
Thanks. Yeah, so what I wanted to talk about was essentially the results which we presented in a paper, which also Lucas is one of the authors. Actually, I didn't write the reference here, but I will send it to you later. So I guess you can share it to everyone. And one thing we discuss in the context of this paper is essentially a generalized version of Wick's theorem. I wrote a generalization here because I guess you can generalize this in different ways, and you, Marek, yourself also talked at some point about some papers that also talked about generalizations of Wick's theorem, and of course they're all different. So I don't claim to have the generalization of Wick's theorem, whatever that could mean. And in the context of this paper, we kind of needed this as a result for applying certain variational methods for approximation of quantum systems. So that was kind of the background, but I won't talk about any of that right now, but more about the technical result of Wick's theorem. So what I wanted to do is to first basically recap what is for me is the ordinary Wick's theorem, and such that one can see what we mean by the generalization. And so in this case, I will consider an operator A, which is a monomial of, let's say, fermionic or bosonic creation and annihilation operators. Basically, all of this works both for fermions and bosons, so it doesn't really matter. So in this case, A will be, something like, I don't know, a certain number of coefficients, and then you have things like a certain number of creation and annihilation operators, so operators of this form. And to try to make this more general, then I will, instead of using these creation and annihilation operators, I will consider their basically Hermitian combinations. So let's say these kind of operators, which are, let's say, for this in bosonic context, are usually called the position operators, and these ones, which are usually called the momentum quadratures. And I will collect all of them in one big vector that I call Z. And so I essentially am saying that this operator A is the most sort of generic expression which contains multiple elements of this Z. So something like this, like a linear combination with coefficient A, I, of a certain product of elements of this Z vector. And I'm summing here explicitly over the I's, but in the rest of the talk, I will just use this Einstein notation where I just write the indices and I neglect this sum for simplicity. But so this is the last time I will write a sum. So we consider an operator of this form. Something's not clear, just ask. And we consider then a Gaussian state, which I call here GS. And that's the second element that we need. And of course, there are many different ways, sort of different equivalent ways of defining what is a Gaussian state, what you mean by a Gaussian state. Here we will use this definition, which is basically that a Gaussian state is any state that can be created out of the vacuum. So the zero here is the vacuum that can be created out of the vacuum by a transformation, a unitary transformation, which is a Gaussian transformation, a unitary Gaussian transformation. And what do we mean by unitary Gaussian transformation? We mean what I wrote here. So essentially something that is the exponential of a quadratic form in these Z operators that I defined above. So basically something, the most general case here is something like exponential of I, so matrix H times 2 times the Z operator. So this is what makes it Gaussian. And one such transformation, unitary Gaussian transformation, has the property that it acts linearly on the Z operators. So if you consider this expression. So you act with u on, sort of adjunct manner on one of these zi, then what you will get out is a linear combination of a certain linear combination of all the other z's, of all the z's. And this combination is given by this matrix that I call S, because in the case of bosons, this is a symplectic matrix. I guess in the case of fermions, it's an orthogonal matrix, so, but I will still call it S. And you can show that basically these unitary transformations can be parametrized by these matrices S. So these unitaries here, I wrote it as a function of S in the sense that it's parameterized by this matrix, which determines how it acts on the Z basis. And this statement is not strictly true in the sense that there is still a freedom of a phase, which is not determined by S. So essentially, for the purpose of this talk, I will basically ignore this issue of the phase. So I will assume that these U's are parameterized by S just for simplicity. The expert of how to keep track of this phase is Lucas. So maybe if somebody has questions about this, we can ask Lucas, and maybe he also can talk about it some other times. But so essentially assume that the results that I find in this talk are correct essentially up to a phase, which I think can also be shown to be just a plus or minus sign. But if you want to really have everything correct, you need to take care of some subtleties due to how to keep track of this sign, which again, maybe Lucas can talk about this some other time. Okay, so we have these two elements, the A and the Gaussian state, which I hope is clear to everyone what they mean. And what we want to compute in Wick's theorem is just the expectation value of A on this Gaussian state. And what you can do is just write it out explicitly. So you bring out these unitary transformations, like in the definition of the Gaussian state, you have this unit transformation that come out. And then you act with these unitary transformations on each of these Z operators. So basically you insert between each Z something like U dagger, which is the identity because of unitarity. And so for each Z, you have, U, Z, U dagger, and you use this expression here to compute it. And this basically brings out a matrix S for each one of these Z operators that you have. So this expectation value can be rewritten as this last line. And one can ask essentially what have we gained in doing this. And so the first thing that one can notice is that this object that appears here is essentially a fixed quantity. It does not depend on the choice of A, well, except on, let's say, the rank of A, how many Zs you have, this number K of Zs that you had in it. But apart from that, it does not really depend on the coefficients that define A. It also does not depend on the choice of Gaussian state because all that information has been extracted in the S. So this only really depends on algebraic relations of how these Zs commute and how they act on the vacuum state. So this is just a k-dimensional tensor, and what we are doing to compute this final expression is just contracting a certain number of indices, which is proportional to this k. Yeah, we're contracting a set of tensors which have a number of indices which is k, and each of these indices has a dimension which is basically 2n, where n is the number of modes that you have in this system, this bosonic or fermionic modes that you have. So already just this expression, you see that for a sufficiently small k, so a small number of Z operators in here, for a fixed small k, this expression is relatively efficient to compute with respect to the number of modes. So it's a polynomial. Like, if k is 2, it's going to be something like, n squared. Computational effort of computing this this expression. And this is already like something non-trivial, because if you just consider this the thing that we were computing to start with, at face value, then this, these are operators and states which live in a Hilbert space, which in the case of fermions has dimension to the end, so exponential. In the case of bosons, it's even infinite dimensional, but even if you truncate the copation number of these bosons, it will also be exponential. So like if you want to compute this expression, like for an arbitrary state or an arbitrary operator in a sort of brute force way, this will have an exponential scaling, while here we reduce ourselves to a polynomial scaling in n, which for especially small k can be easily done. And this is essentially like a result of the fact that we have this expression for the Gaussian states. So this linear scaling in Z of this transformation means that when you compute this transformation on the A, it does not increase the number of Z's that appear inside here, or does not make them become an arbitrary polynomial in Z. So you maintain this scaling structure. So that's the first thing that the first step that one can make to improve your the ability to compute these expectation values with Gaussian states. But the second thing that one can notice is that actually for creation annihilation algebra, so for bosons or fermions, you can convince yourself that this expression for any even k actually decomposes into a bunch of 2-point expressions. So like this whole product of z's can be split into a list of products of 2 of the z's, 2 at a time, and then each one individually you take the expectation value on the vacuum state and you multiply them all together, and then you sum over all the contractions, which basically means summing over all possible ways of doing this. And so you see that this simplifies even further the calculation, because then this reduces to all the quantities to just one object, which is this thing that here I call gamma. So it's this 2-point correlation function between two Z operators on the vacuum state. And if you plug this back into the previous expression and you assume that essentially you're computing the expectation value of basically a product of k objects of this form. So each object is a linear combination of z's. So you don't have, like before, an arbitrary polynomial with arbitrary coefficients a, but you assume you have a product of linear objects. Then you expand it like before, and then you can see that inserting the composition, then this will break down into again a sum of products of objects of this form. And these objects basically are a matrix. They have 2 indices, and they are the only objects on which this expectation value depends. So this simplifies your computational cost even further, because basically you only have to compute objects which are n squared dimensional in scaling. And of course, this does not completely solve your problem for arbitrary large k, because then you have the number of contractions that you have scales very badly when you increase this k. But at least for bosons, for sufficiently small k, this helps. And for fermions, I think this helps even more, because you can see that this expression here can be re-expressed in terms of the Pfaffian of a certain matrix, of this matrix here probably, and which is something we discussed the previous time that can be computed efficiently. So this type of results simplify even further the computation. But the point is that this thing relies explicitly on the commutation or canonical commutation and anti-commutations of the fermionic and bosonic operators. Okay, so this was kind of I tried to give my perspective on the ordinary Wick's theorem, and hopefully it will be clear like where I want to go from here now. So now, what would I like to generalize? in this generalized Wick's theorem. Okay, so if you have any questions about what I said before, maybe that's a good point to ask. And continue.
Okay, I restarted the recording.
Okay, can you still hear me?
Yep, we can hear you.
Okay, because okay, my iPad looks a bit frozen, but okay, now it's working. Right. Okay, now I want to talk about what I would like to generalize. And the first thing that I would like to I would like to generalize actually two things. So the first thing that I would like to generalize is that I would like to consider expressions of this form, where now the states on the left and on the right are two different Gaussian states. So they're still Gaussian states, but they're two different ones. And this is useful already if you want to, for example, consider some kind of ansatz class where you have superpositions of Gaussian states, like linear superpositions. Then when you try to compute expectation values of your Hamiltonian, for example, on these states, then you will immediately come across terms of this kind. So this is a relatively generic expression that you do come across. And so that's the first generalization that we would like to make. And you can convince yourself that computing this thing is equivalent essentially to computing something of this form. And this is because if you just consider these Gaussian states, again, as I wrote them before, in terms of unitaries acting on the vacuum state, this will be like something like this. Then you have your z's. And here on the right, you have a different unitary. And then you can commute this unitary past all of these z's using basically the same technique that we discussed before. So each of these commutation will bring you out a certain factor s that you're multiplying. But again, so at the cost of taking linear combinations of your final result, this is not changing anything. And so, and once you bring the u to this side, you're left with something like this. And then these two unitaries, you can see that the product of two such Gaussian unitaries is again another unitary. And actually the matrix that parameterizes it is just the product of the two corresponding matrices. So essentially you can reduce anything of this form to something of this form. So basically what we are interested in is taking the expectation value on the vacuum state of a product of certain number of z operators and one Gaussian unitary. So this is already something more than the ordinary Wick theorem that I talked about before, but it unlocks some useful applications. And the second thing that I want to generalize, or could be useful to generalize, is that I would like to do this not just for the bosonic and fermionic algebras, but for arbitrary Lie algebras and groups. So I kind of on purpose use this rather abstract notation where instead of talking about the creation and annihilation operators, I talk about these Hermitian operators Z, and instead of talking about explicitly the exponential of some quadratic expression, I talk explicitly about this in this abstract way of these Gaussian unitaries. And I did this on purpose because you can see that this is a relatively general structure. So in principle, you can do perform this whole procedure for any kind of unitary group of unitaries U, which give you a unitary representation on your Hilbert space of a certain Lie group that we call G. So for every element small g of a certain group big G, I will have a unitary U. So previously the group was these symplectic matrices or orthogonal matrices S that parameterized our unitaries. Now consider an arbitrary matrix or arbitrary group object G that parameterizes U. And then these Z operators that I had before are now generalized to being the generators of the Lie algebra corresponding to the same group. So if you have a unitary representation of the group, you will automatically also have a, let's say, anti-Hermitian representation of the algebra. So these Z operators are now anti-Hermitian operators on the Hilbert space, which represents element of the algebra. And in this language, these Gaussian states that I talked about before as unitaries acting on the vacuum can be represented as states parameterized by the group elements, which are defined by the corresponding group unitary acting on a certain reference state that I now call mu, and I will explain later how you have to pick it. This mu should be the lowest weight state of the representation, and I will say later better what I mean by this, but it's a certain fixed state that one can pick out of the way the representation works. So all these objects generalize in this way to an arbitrary setting, and you can see that this is consistent with what I wrote before, because basically you can see that I mean, before I cheated slightly, but like you can rewrite everything I wrote before. Like the Z's of before are not exactly the Z's of now, but like you can write everything that I did before as, these basically pairs of creation and annihilation operators generating the unitary Gaussian group, and so everything is matching as it was before. And what I want to compute again is something of this form, where now these Z's are arbitrary algebra operators basically, and these Gaussian states on the left and on the right are arbitrary states created out of the reference state mu by two different group unitaries. So this is kind of the two generalizations that I would like to make. And then like maybe one should stress what does not generalize. And what does not generalize is that this discussion that I did here, basically this part on this product expectation value on the vacuum splitting into this contraction structure, this is actually just a property of the bosonic and fermionic algebra. So for an arbitrary algebra, so for this second generalization, this will not hold.
So the idea is that it will work nicely for semi-simple Lie groups, or just in general for Lie groups?
No, I will assume that the Lie group is semi-simple, yes.
Okay, yeah.
And but this thing is not related to the semi-simpleness.
Yeah. So
this really works essentially if basically just for these bosonic and fermionic algebras. So if you have the commutator is the identity, it's proportional to the identity.
Okay, commutator identity, yeah. And one maybe stupid question, but in some way, sometimes people say that somehow the algebra doesn't belong to the manifold in some way. So in terms of representation, you were saying that the formula that we have now, this is evaluating the algebra, right? Because can I construct this kind of stuff geometrically in other way than just the tangent space, or like the geometric interpretation of the correlator that we have? Is this already the tangent space interpretation, or?
No, so strictly speaking here, I will not talk so much about tangent spaces. What is correct, what you're saying is that the Lie algebra is essentially the tangent space of the Lie group. So if you consider an object, if you consider the states defined in this way as your manifold of states, then there's a certain set of states parameterized by G, then you can see that the tangent space to this, so the tangent space at G of your manifold would be given by essentially objects related to the algebra. So this is related to the group, and this will be objects related to the algebra. So essentially objects of the form Zi. So acting with Z on your element will give you an object in the algebra.
Yeah, yeah.
So in this sense, this kind of objects appear naturally as essentially overlaps between different tangent vectors. So if you're doing this kind of tangent plane analysis and geometric, you want to compute metric or symplectic form, whatever of your manifold, then you will for sure encounter objects of this form. So in this sense, this is quite natural. But this is also even more useful because often also the Hamiltonian of if you're embedding this, inside a many-body quantum many-body problem, also the Hamiltonians that you have usually a simple structure in terms of a few operators. And so they can, in the case of bosons or fermions, they can also be written as low order polynomials in creation and annihilation operators. So they also have this kind of structure. And you can construct several other examples also with spins and so on, where you have a manifold where you have an algebra of the tangent vectors, and that the Hamiltonian is a polynomial in these algebra operators. But this is not necessary. Like, your Hamiltonian could be anything, and there is no reason why it should be related to the algebra. I mean, that's more of a question of choice. Like, probably you should choose, if you choose a manifold whose algebra is related to the Hamiltonians you're interested in, that's probably a good choice, but that's up to you.
Yeah, okay, thanks.
So yeah, this is kind of the relation very quickly to that tangent space discussion, but yeah, I was not planning to talk about that right now.
Yeah,
so,
of course. Yeah, but that helps already. Thanks.
But yeah, no, I'm just saying it could be interesting to talk about this next time. Yeah, so okay, so this thing that the Wick expansion only depends on the 2-point function, this is very special to fermions and bosons, so this will not generalize in this generalization here. Okay, so now in order to get the result that I want to discuss, I would like to introduce a bit more in detail this whole group and algebra representation theory. So we will need a couple of technical results and eventually get the final result for the expectation value, but shouldn't take too long. So I hope you can bear with me. So as I said, we are considering a representation on our given Hilbert space of a group given by some unitary operators. So they are a group in the sense that, the representation of the group in the sense that, as I kind of also wrote before, if you take the product of two different unitaries parameterized by two different group elements, this will be equal to the unitary related to the product of these two group elements. Again, in general, in some cases, this will be up to a phase, which as I said, I will more or less ignore. And we have some elements Z, which are some operators, which again act on the same Hilbert space. They will be anti-Hermitian operators in this Hilbert space, and they represent objects in the algebra of the corresponding, let's say, in the Lie algebra corresponding to the Lie group. As before, we have that the action of these group elements on the Lie algebra elements in this way is a linear action given by a certain matrix S, to use the same notation as before, S of G, which would depend on these group elements. And this, again, this matrix can be constructed essentially out of properties of the group. So this will be the adjoint representation of this group element G. So you can just assume to represent all these objects G in terms of a matrix in the adjoint representation, then it will become a matrix group, and you can assume S to be just this matrix. Right, and if you want to be more precise about how to compute this S, basically, if you assume that your group element, so G, can be written as the exponential of some object in the algebra. So of some set of coefficients will be determined by a set of coefficients that give you an object of the algebra. Then essentially you should consider the structure constants of the algebra. So if you consider the commutation relation between two okay, so maybe going a bit slower so that everyone can follow. Like every algebra elements, their commutator will give again a linear combination of algebra elements. So this will define certain coefficients, which I guess I can call K. So these coefficients here are usually called the structure constants of the algebra because they define the commutational relation between any arbitrary element of the algebra. So this kind of is a fixed fundamental property of your algebra. Then every group element that is, let's say, sufficiently close to the identity or connected to the identity can be represented in this way as the exponential of something in the algebra. So a linear combination of objects in the algebra. And if you have this decomposition, then you can show that the adjoint representation of G is a matrix, which is the exponential, say, of another matrix M, where such that the matrix elements of let's call them Lj of M are given by this. So you have that the combination of these coefficients that determine your G and the structure constants give you a matrix, which when you exponentiate it again, will give you your this thing that we call S, this matrix we call S. So anyway, this maybe I got a bit taken off track just to say how one can compute explicitly these objects as. But what's important is essentially this result here, that the action of the group on the algebra gives you a linear combination again of the algebra.
And is it G equals C I Z I, or is it U of G maybe or something?
This
yeah, so
yes, sure. Like if you assume that these
and more generally you would just okay, so maybe you were talking about the element of the Lie group. Yeah, okay.
Yeah, you can talk about it in terms of the representation, like here, or you can talk about it more abstractly, like you can also define an exponential in the abstract group. So it's meaningful to say also that each G in the group is equal to the exponential of an object in the algebra. But I guess it's more correct to write it like this because I had kind of defined these Z's as being the representation of the algebra. So they are Hilbert space operators. Then also on the left, you should have a Hilbert space operator. But yeah.
But I could also talk about the Lie group. It's abstract Lie algebra, and then have an exponential map, and then just talk about two different representation U of G and the adjoint. Yeah.
Yeah, exactly.
Okay.
Okay, so now I would like to just quickly go through some results that one can derive. I mean, this is well-known results from Lie algebra theory that, however, maybe are not so simple to derive, but I will just present the results here on the structure that these algebras have. And for this here, I assume that this group is semi-simple. This is like a technical assumption. It basically just means that there are no non-trivial ideal, that the algebra does not have any non-trivial ideals. So sub-algebras that such that the commutator of every element of the algebra with this sub-algebra is again in the sub-algebra, something like this. But anyway, this is a technical constraint on the algebra. And if this algebra is semi-simple, then you have the following series of results. So first of all, you have that these ZIs, by definition, are a basis of the algebra. So all elements of the algebra are linear combinations of this ZI. But out of this algebra, you can pick a subspace, which is called the Cartan subalgebra, which is made up of L elements. which I will call h of A. So this subalgebra has a dimension L, so it has a basis which is made up of L elements, which I will pick to be this HA. So these HA are elements of the algebra, so they're also linear combinations of the Zi. So each HA is some kind of linear combinations of the Zi defined in a certain way. And the way that this subalgebra is defined is that all these HA basically commute with each other. So basically, this is the largest possible choice of a subalgebra such that each element in this subalgebra commutes with each other. And this defines this so-called Cartan subalgebra. And of course, there are many different ways you can, there are different choices that you can make of which elements you include in subalgebra, but there will always be a maximum number L of them. Then once you've chosen this Cartan subalgebra, you can also show that there exists a certain number of vectors and eta. These are real vectors with real entries and of dimension L. So each of these etas is composed of basically a list of L real numbers. And these are called root vectors, roots of the algebra. And for each eta, so for each root, there exists an operator E that I call E of eta, which is again an element of the algebra. And this is the sort of root operator corresponding to this root. So these E's are also elements of the algebra, so they're also linear combinations of the Z, except these could be linear combinations with complex coefficients. So the E's do not necessarily respect to this anti-Hermitian structure of the original sets. But anyway, you have an E for each eta, such that basically the condition on this E is that the commutator between every HA, every element of the Cartan algebra with E, is proportional to E again. So with a proportionality constant, which is I times eta A. So let's say the corresponding element of the eta. So basically, these E's are the eigenvectors of the action of the H in terms of the commutator. So this map has some eigenvectors, and each of these maps for each of different choice of A, they commute with each other, so they have a common basis of eigenvectors, and these eigenvectors are these etas, this E eta, and the eigenvalues are the corresponding eta A. Right, so you have a list of roots and a list of corresponding root operators, and you can show quite quickly that for every eta, also minus eta should be a root of the algebra, so they come in pairs, eta and minus eta. And so you can basically pick a conventional ordering of these roots and say, I divide them into two sets, which I call delta plus and delta minus. And I say, if I put eta into this set, then I must put minus eta into the other set. So I split them into each of these pairs into two different sets, such that the union of these two sets gives me the full space of roots, and that they are disjoint, and if eta is in one set, then minus eta is in the other one, basically. And so I call these ones positive roots and these ones negative roots. I mean, this is again a conventional sorting, but you can do it in a consistent way. Okay, finally, you can show that all these operators taken together, so all the Cartan subalgebra operators plus all the root operators for all the roots, they together span the whole algebra. To be more precise, they span the complexified algebra in the sense that in order to recover an arbitrary algebra element, you might need to use complex coefficients again. So complex linear combinations of what these elements give you any complex linear combination of any algebra element. So in this sense, they allow you to span the whole algebra. Okay. So finally, now we can introduce these weight vectors that I had mentioned at some point. And basically, these weight vectors are defined once you introduce a representation of the algebra. So all that I said before is again true at an abstract level. So it only bases itself basically on this commutation, really on having this commutation structure. Now I actually assume that I have a representation. So each of these vectors or each of these objects is defined as a operator on a certain Hilbert space, for example. So given the representation, I can define the weight vectors mu basically as the eigenvectors of the operator's H, the common eigenvector basis of the operator's H. The operators H all commute, so they have a common basis of eigenvectors, which I call mu. And each mu has an eigenvalue, is an eigenvector of all the operators HA for every A. And the corresponding eigenvalue I call mu of A, I mu of A, because it's anti-Hermitian. So these are the weight vectors. And you can show that there exists a unique weight vector, which is called the lowest weight vector, which has the property that it is annihilated by all the root operators eta for every eta in the negative root subspace. So when you act on it with E eta for a negative root on this given mu, it will give you 0. And there is only one mu, let's call it mu 0, that does this. And this is called the lowest weight vector. So when I define Gaussian states, I define them in this way, and here we assume that this unitary, this group unitary is acting on this fixed lowest weight state. So basically all that I've said here, like you can see that this is all like, there are many different choices of how you can do this. Like you can pick different choices of Cartan subalgebra, you can pick different orderings of the root into positive and negative and so on. But it turns out that all of this construction is, all of this, the possible different choices are essentially unitarily equivalent to each other. So going from one choice to the other, you just basically adding another unitary to how you define your states. Okay, so having gone through all this construction, I hope I didn't confuse you or bore you too much. We can finally compute this expectation value that we were aiming for, which in the most general case now has this structure, just to remind you. So this comes from taking the expectation value of an arbitrary polynomial of algebra operators on two different Gaussian states, or generalized Gaussian states, on the left and on the right. So how will I compute this? Well, first of all, I will again assume that this group unitary or group element is sufficiently close or connected to the identity such that I can express it again as a exponential of an object in the algebra, which I will call in this case A. Now, an object in the algebra, as I said, can be expanded as a linear combination of my Cartan elements and my positive root elements and the corresponding negative root elements. So I write out explicitly this expansion in terms of some coefficients, which I call K0 for the Cartan element, K plus for the positive roots, and K minus for the negative roots. And I write it in this way. And what I would like to do now is essentially to split this exponential into three exponentials. So into three terms, T plus, T0, and T minus, such that the T plus only contains elements from the positive roots. So only these E plus type operators. And T0 only contains the Cartan elements, so something like this, exponential of only Cartan elements, and T minus only contains elements of the negative root spaces. So obviously these are matrices or like matrix objects, so you can't just split this exponential into three exponentials for free, but there must exist other basically other sets of coefficients they call A. So these A's here are different from the K's, but there must exist these coefficients which are a function of this case, such that the operator splits into these three. And this is some sort of generalized version of normal ordering your operators in the boson or Fermi picture. So this is essentially doing some what you could call a BCH, the composition of your exponential into three pieces. And so here, how exactly you need to do this decomposition basically depends on the algebra that you're dealing with. So for some, commonly used algebras, these BCH decomposition basically are known. So you can just pick off formulas from the literature. For example, for this boson or Fermi algebras, you can just pick them out of the literature. If you have a arbitrarily complicated algebra that for some reason you're dealing with, then you might have to find another way to derive this BCH decomposition, which might be a bit complicated. But I mean, in that paper, we also present some generic way of deriving it. But I mean, that's maybe too much. I won't go into it now. But basically, once you have this decomposition, you're almost done, in the sense that then you just need to observe that this T minus object that you have here annihilates the lowest weight state that you have here. So this is what we called mu zero before, because T minus is just the exponential of something that only contains negative roots. So, and we said that the negative roots annihilate the ground state. So the lowest weight state. So you will have that T minus on mu zero is 0 or is 1, because it's the exponential of something that annihilates mu zero. And in the same way, T plus kind of preserves the lowest weight state on the other side, because it's easy to check that basically the positive roots are just the dagger of the negative roots. And finally, T0 has mu zero as an eigenstate. So here you will have some number, because again, all these T0 only contains these Cartan operators, which have mu zero as an eigenstate. So this will basically be also an eigenstate where alpha will just be e to the times the eigenvalues of this HA on mu zero. So it will be some phase given by these expressions that just appear here. So these three objects separately behave very well with the mu zero. The only thing that is left is that we need to commute them around a bit past these Z operators. And to do this, we use this final last result. And that is that T minus is not a unitary, because it is given by the exponential of something with these E operators, which I said before are not anti-Hermitian in general. It's not unitary, but it still acts on the Zi and the algebra elements in a linear way. You can check this, that this action of the Ti on the Zi is again given by a certain linear map R, which can be computed in a very similar way to how we computed this adjoint representation before. So you can have these linear operators that appear here. And so now we can finally do the last calculation, which is to take this expression, which is what we wanted to compute, split the U into 3, like I said before, then commute this T minus to the left, sorry, to the right. And again, each time it commutes through a Z, one of these R matrices will pop out. And essentially, once we have this expression, we can just use the relations that I said before. So this T minus on mu doesn't do anything. This T plus mu on the left also doesn't do anything. This T0 brings out a phase, which is given by this. And these R's are here. And finally, you have this expression, which is what we had in the original Wick theorem. So you can see that basically also in this case, the whole expression can be reduced to an object which is basically a contraction of a certain number of k of indices, each one 2n dimensional, with an object which is fixed and determined by the algebra relations. You can also see that basically this phase that you have here is essentially what you would get if there were no z operators here. So in that case, this is just the expectation value of your original unitary on mu. Or, if you want, if this object came from the expectation value on, two states, this is just the overlap of the two states. So basically you have the overlap of the two states times something that is, again, just basically original big theorem expression. So these z tildes, you can see them as, just a rotation in terms of this matrix R of your original z operators. And here you're taking an expectation value of a certain number of them on a fixed state. So if all of this you did it for the algebra of bosons and fermions, then this would, again, here the normal big theorem would apply in all its glory, and you can decompose this into 2-point functions. If you're using an arbitrary algebra, which is kind of the second thing that I wanted to generalize, then computing this expression, might be a bit more tedious, but it will still be something that scales polynomially in the number of modes or algebra elements that you have. So it's, again, something that can be done. And that's it. So basically this expression is not as difficult as it might look if you want to compute it sort of brute force. So that's basically the result that I wanted to get at, and that's what I planned to say. As I said, this what I told you was all in one paper, which maybe I can quickly show you if I have a minute, but maybe I should stop sharing from here.
So still one question, Tommaso?
Yes.
So if I had a difficult state some wave function and I would have this low rank portion of the correlation tensor, then basically your formulas could give me those kind of scalar products and so on for Gaussian evolutions applies to those states, right? Those kind of things I could maybe use it as well.
So your state is a non-Gaussian.
So yeah, I'm wondering. So as you said, I mean, in two cases, it collapses so that the final kind of correlation portion maybe has a big decomposition, but for a general Lie group and so on, maybe it doesn't hold.
Yeah.
But then I guess you can still work with that given those numbers, right? So
yeah. If you're, for example, here your mu is not your vacuum, but some arbitrary complicated non-Gaussian state, then you can still compute this object, if you have a small number of z's, I guess.
Yeah, so basically I would have to query it and assume that somebody gives me those numbers correctly, but then I could also try to consider those different Lie group representations acting on those states and try to maybe work with that as well. So I'm wondering, for example, if you consider general Lie group theoretic coherent states, I guess like the only difficulty is similar like with a general many-body state, that if you get the access to those numbers, you can work with them, right? Is that kind of so I'm kind of wondering where's the transition from bosonic, fermionic to general coherent states? And I'm wondering if it's just similar to having an arbitrary state and querying those numbers and then working with them, or do you have more structure?
So the difference, I guess, is that these kind of object, or let's see, this kind of object for the case in which you have, okay, so let's say in the case in which you have bosonic algebra or fermionic algebra, we said this is easy, it splits into these contractions. In the case in which you have some kind of algebra structure that is not the bosonic or fermionic algebra, this is more difficult in the sense it doesn't split in this way, but you can still evaluate this object based on the commutation relations of these sets, essentially, because you can decompose each z into a combination of your Cartan and your E's into linear combinations, and then you have to play around with the commutation relations and bring them into normal ordering, and then you will finally reach some expression for this. So essentially, computing this expression will probably be very complicated and tedious for arbitrary algebra, but you essentially can do it just exploiting the commutation relations. While in the third case, which is this mu is like an arbitrary state in the Hilbert space, then I think the only solution that you have is to compute this object as a inner product in Hilbert space, which is something that in general might scale much worse.
Yeah, and I think there's also the problem. I just realized that this t plus t minus doesn't work the same way. I mean, you would still have the insertions because you said it's a generalized normal ordering, but with respect to those kind of base vectors. But a general psi might not be normal ordered with respect to your Cartan decompositions as well. So there would be some leftovers still. So not
right. Yeah.
Not exactly.
So I thought, I thought you were talking about just taking an ordinary Wick product in which here you have the same state left and right. In that case, what I said would apply. If on top of this you also have this object in here, then you would get stuck, let's say, one step earlier, because then here you need to get rid of these t plus and t minuses.
Also this, yeah. But then sometimes maybe there are states which have like simple structures, like those topological states and so on, but I think they have simple algebraic excitations and so on. So sometimes without knowing the wave function, if you're in some phase, maybe you can know something.
So I think one idea that I thought about for a while but never really implemented is that if you consider like a spin system, then the corresponding structure here is you have here some SU2 type operators, basically Pauli rotations, and it turns out that this whole structure is compatible with putting here, instead of mu, basically some MPS, for example, some tensor network state. Then doing the whole contractions would be efficient with, for example, arbitrary matrix product states there. That's something that I thought about. That, okay, maybe I didn't explain in detail now how it would work, but I think there are special cases in which if you pick the algebras in a certain way and you pick the states in a certain way, there are more general cases than this in which things would combine and work out.
All right. Okay, so let me post the video and then we find the paper and just add the link later also in the description.
Yeah.